Want to outsmart the next $1.5 billion crypto hack? The recent Bybit exploit got me thinking, how do we secure multisig smart contracts against the next big attack? Today I'll break down past multisig flaws, analyze real-world hacks, and use best practices to build unbreakable multisig program on Solana. Multi-signature smart contracts are designed to enhance security by requiring multiple approvals for transactions. However, flaws in their code have historically led to devastating hacks. And going back to February 19th, 2025, Bybit, one of the top crypto exchanges, suffered the biggest single hack in crypto history. We're talking $1.5 billion in ETH yanked from their multisig cold wallet, faster than you can say smart contract audit. During a routine transfer from Bybit's multi-signature cold wallet to a warm wallet, attackers later tied to North Korea's Lazarus Group manipulated the transaction process. They executed a sophisticated attack that masked the sign-in interface, showing the legitimate address while altering the underlying smart contract logic. The hackers used a technique called masking, coined by Bybit CEO Ben Zhou, masking the UI to show a benign transfer while the signed payload swapped implementation to their malicious contract via delegate call. Once in control, they drained more than 400,000 ETH, 90,000 STETH, and more, totaling in $1.5 billion, flowing to 48 plus addresses in a blink. This wasn't just a smart contract flaw, it was a human plus tech exploit. And here are my takeaways from this situation. UIs lie. Signers must check the raw transaction hacks, not just the pretty dashboard. Delegate call should be avoided, instead use proxies carefully or stick to static logic. Use air-gap signers. Offline signing devices mean no internet, no malware, no surprises. Please like and subscribe to let me know you find this content useful. And I'm going to remind you of some notable multisig-related hacks along with security lessons for building secure smart contracts. So, starting chronologically from the DAO hack in 2016 on Ethereum. While not a pure multisig hack, the DAO, a decentralized investment fund on Ethereum, used a multisig-like structure for fund management. A reentrancy flaw allowed an attacker to drain 3.6 million ETH, which is approximately $9.7 billion nowadays, by repeatedly withdrawing funds before the contract updated its state. So the attacker's contract called withdraw repeatedly via its fallback function before the balance was reduced, exploiting the unchecked external call. In other words, he performed a reentrancy attack on the multisig execution function. I talk more about the consequence and whether the hacker was found in this video. Lessons we've learned. Use a two-step withdrawal process. First, mark the transaction as executed, then transfer. Ensure that the state is updated before external calls. Next was the parity multisig hack in 2017, resulting in more than 500,000 ETH permanently frozen, which is about $1.6 billion nowadays. The smart contract relied on a library with an unprotected init wallet function that was accidentally left public. This function lacked access control and allowed anyone to reinitialize the wallet and claim ownership. Which is what happened. The attacker reinitialized the wallet, made himself the owner, and destroyed the contract, locking all assets stored in the multisig contract. Our lessons learned as Solana devs. Never allow the reinitialization of critical accounts. Use the owner PDA model in Solana to prevent unauthorized control. The Banker multisig exploit in July 2018, when Banker, a decentralized liquidity protocol on Ethereum, suffered a $13.5 million hack due to a flaw in its multisig wallet used for managing upgrades. The delegate call to an untrusted contract allowed the attacker to execute malicious code in the context of the multisig, draining funds. The multisig lacked proper validation of the new contract address. Lessons learned. Never allow unrestricted delegate call to an external contract, as we've just witnessed how history repeats itself almost 7 years after this case. Validate all contract upgrades with strict security reviews. Require multiple approvals before allowing upgrade execution. This ensures contract upgrades go through a governance process and are validated before execution. In October 2021, the Cream Finance multisig flash loan attack occurred. The multisig approved lending contract relied on an unverified external price oracle, allowing the attacker to manipulate asset prices artificially and resulting in loss of $130 million. The attacker used a flash loan to manipulate the oracle's reported price, inflating asset values. They then borrowed an excessive amount and drained liquidity before the system could react. Since the multisig trusted the manipulated price, it allowed the transaction without safeguards. Lessons for Solana multisig security. Validate external oracles before using them for critical operations. Implement price sanity checks to prevent extreme fluctuations. Use time-weighted average pricing instead of relying on a single price snapshot. This ensures loans are only approved when the price is within a reasonable range. Moving on to Ronin Bridge and its two multisig hacks in March 2022 and August 2024. First Ronin Bridge hack happened because Ronin's validator multisig with threshold of 5 out of 9 was too centralized, making it vulnerable to key theft. Private key compromise via social engineering resulted in losing $625 million. Ronin used a proof of authority multisig that required 5 out of 9 validators to approve transactions, and those 5 private keys were compromised through a phishing attack, and the attacker was able to execute 2 massive withdrawals before detection. Shocking is that the breach wasn't noticed until 6 days later, when a user reported a failed withdrawal. Lessons learned are as follows. Centralized storage of private keys defeats multisig security. Use hardware wallets or multi-party computation. Enforce hardware security modules for the key storage. Regularly audit and revoke unused permissions. This ensures that the multisig never operates with an unsafe number of signers. The other case is the Ronin Bridge exploit, when the multisig governance update introduced an uninitialized variable, lowering the approval threshold to 0, which led to loss of $12 million. A bridge upgrade deployed via multisig governance introduced a bug where total operator weight wasn't initialized. Because the contract inherited a previous weight value of 0, any transaction signature became sufficient to approve withdrawals. Lessons learned from this situation. Always initialize critical variables during smart contract upgrades. Seems obvious. Test governance changes rigorously on DevNet before deployment. Implement strict upgrade review processes. Limit daily withdrawals to prevent a large loss. Not all of these cases are pure multisig hacks. Some involve vulnerabilities related to multisigs, but are not direct exploits of multisig mechanics. But we still need to be aware of these cases. So here are final takeaways for a secure Solana multisig before creating one. Prevent reinitialization. Validate transactions before execution. Update state before transfers to avoid reentrancy issues. Restrict sign-in modifications. Ensure decentralization. Unchecked external calls remain a top vulnerability. Be mindful of Oracle dependence. Remember of governance risks. Don't forget about arithmetic safety and consider whitelisting trusted programs. These lessons ensure a robust and attack-resistant multisig system on Solana. Now we're diving in the Solana Anchor multisig program creation, trying to implement as many of the best practices as possible. Feel free to share your experience and tips in the comments. But first, I have to be honest with you. I've overestimated my enthusiasm of showing the flow of how the program is done. So now I will just walk you through the multisig program I've created. This program supports initializing a multisig, proposing transactions, transfers or threshold updates, approving them, removing approvals, and executing them securely. So the program starts with initialize, setting up the multisig and escrow. It takes an admin, a list of approved signers, a threshold, minimum approvals needed, and an initial balance to fund the escrow. The context uses PDA's multisig with seed multisig, as you can see, for governance, and escrow for SOL storage. The admin signs and pays rent. The multisig state tracks the admin, signers, threshold, and nonce. Escrow holds the balance and bump. The handler sets the state and transfers SOL to the escrow. And this is the simplified version of a program where only SOL transfers happen. Talking about safety, using init with PDA seeds ensures these accounts can't be reinitialized. Once created, they're locked to these addresses. For arithmetic safety, we check threshold is less or equal to approval list len to avoid invalid setups. We could also verify initial balance feeds within escrow's capacity. I have to mention that admin in this program gives a bit of centralized vibe, but we'll discuss in the end how it can be improved. Propose instruction lets an approved signer propose a transfer or threshold change. It takes a nonce for uniqueness and transaction type enum and an auto-approve flag. The context creates a transaction PDA, linking it to the multisig. The transaction state stores the action type, approvals, and execution status. Transaction type defines transfer or threshold change details. The handler validates the propose and sets up the transaction, optionally auto-approving. Talking about safety, the nonce in the seed prevents duplicate proposals at the same address. And talking about validate transactions before execution, we check the proposer's authorization and validate amount target and new threshold upfront. And here we don't forget about arithmetic safety, ensuring amount is more than 0 and new threshold is less than or equal approvals len, which avoids invalid states. Moving on to approve instruction, which allows a signer or admin to approve a transaction identified by nonce. The context ties the signer to the transaction and multisig PDAs. The handler adds the approval if the signer is authorized and hasn't approved yet. Also here we're checking if the transaction hasn't been executed yet, which ensures that we don't approve completed actions. Moving on to delete approval instruction, which lets the admin remove an approval from a transaction and is useful for correcting mistakes. So this instruction was inspired by the Bybit case, where probably if this instruction has been there, after approval, one of the signers realized that there's something wrong, they could delete their approval and give some extra time for solving this situation and contacting other signers to prevent their execution. Here, the context restricts this to the admin linking to transaction and multisig. The handler ensures the admin is authorized and the transaction isn't executed yet. And the execute instruction runs the transaction if enough approvals are met, handling transfers or threshold changes. The context includes the authority, transaction, multisig, escrow, and system program with remaining accounts for the transfer target. The handler validates everything, executes the action, and updates state. So talking about safety and updating state before transfers, here the transaction executed is true, set before the transfer to block reentrancy attacks where a malicious target might call back into execute. The nonce increments after success, keeping it tied to completed actions. And also there are checks for authority, execution, status, nonce and thresholds, which ensures safety. So now we can do the key sync, build, and deploy the program to the DevNet. And now we can go to SolScan and check that the program was deployed. And also we can run the integration tests to check that the instructions work as expected. That's it. Also, we all know that the sky's the limit and there's also some space for improvement. And I'd like to mention that this program can be improved by doing the generic transactions that support any Solana instruction like token mints, using invoke signed instead of limiting to transfers and threshold changes. So doing the program functionality more generic. What else could be done is adding the owner sequence number to track signer changes and prevent stale transactions, as well as unique owners check using a loop to ensure no duplicate signers are on the list, enhancing security. And PDA signing using multisig signer PDA for all CPIs, not just escrow, for broader authority. So these upgrades would make this multisig program more flexible and secure. Also, I will be really happy to hear some improvements, ideas from your experience in the comments. That's it. What do you think of this program? Let me know if I missed anything. Wishing you safe coding. Thanks for watching. Bye.